In this video, we're going to talk about equilibrium, but within the context of chemistry. So what is equilibrium? Well, let's say we have a reversible reaction where A can convert to B and B can convert to A. Equilibrium occurs when the rate of the forward reaction, that is A going into B, is equal to the rate of the reverse reaction. When these two rates are equal, the concentration of A and B will be constant. There's not going to be any net change. And so that's when we have a case of equilibrium, where the concentration of A and B are not changing because the rate of the forward reaction is equal to the rate of the reverse reaction. Chemical equilibrium is a form of dynamic equilibrium. It's not static because things are happening. Even though a system may be at equilibrium, the reaction is still occurring. A is converting into B, B is converted back into A. So we still have a reaction, but the concentrations of A and B are no longer changing at equilibrium. So we have a case of dynamic equilibrium. Now, to illustrate this concept, let's say we have two cities. On the left, we'll call this city A. On the right, city B. Now, let's say that city A has 1,000 cars. And we're going to say that city B has 2,000 cars. And let's say connecting these two cities is a highway. And on average, each hour, 10 cars travel from city A to city B. And each hour, let's say that 10 cars travel from B to A. So we could say that the rate of the forward reaction is 10 cars per hour. And the rate of the reverse reaction is also 10 cars per hour. So if each hour 10 cars is going from A to B and 10 cars is going from B to A, will the number of cars in city A and B change? The answer is no, because if A loses 10 cars each hour, but also gains 10 cars each hour, the total number of cars in A is going to remain constant. The same is true for B. These two don't have to be equal, but at equilibrium, the concentration of A and B are no longer changing. It's constant. And so that's what happens when a reaction is at equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. And at that point, the concentrations of A and B are no longer changing. Another way in which we could visually show this concept is by the use of a concentration profile. So this is going to be a graph with the concentration of the reactants on the y-axis and time on the x-axis. So we're going to put A in red. Let's say initially we put 1 mole of A inside a container of a fixed volume, and there's no quantities of B in this container. So initially, if we only have A and no B, the reaction has to go to the right. It can't go to the left because there's no B to convert into A. So that's what's happening initially. If we put 1 mole of A, let's say in a 1-liter container. As the reaction goes to the right, the concentration of A is going to decrease over time. The concentration of B is going to increase. So A is going to decrease. It's not going to go to 0, but eventually it will become constant. B starts from 0 and then it increases. B becomes constant when A becomes constant. When A stops decreasing, B will stop increasing. Now the point where the concentration no longer changes, that's where we have a case of dynamic equilibrium. So whenever the concentration of A and B, when it becomes horizontal in this graph, that means it's not changing anymore. At that point, the rate of the forward reaction equals the rate of the reverse reaction. And so they're equal at that point. So now let's plot a graph that shows the rate of the forward reaction and the rate of the reverse reaction. So we're going to put the reaction rate on the y-axis, time on the x-axis. So the rate of the forward reaction is equal to K1 times the concentration of A. As the reaction goes to the right, A is going to decrease. And as A decreases, the rate of the forward reaction is going to decrease. So initially, the rate of the forward reaction is going to start at a high value, and then it's going to decrease over time. Let me draw that better. And eventually it's going to be constant. Now, as A decreases, we know B is going to increase. And the rate of the reverse reaction is dependent on the concentration of B. It's K negative 1, that's the reverse rate constant, or the rate constant for the reverse reaction, times B. So as B goes up, the rate of the reverse reaction is also going to go up. So I'm going to put that in blue. Now eventually, the rate of the forward reaction is going to equal the rate of the reverse reaction, which it does here. So at that point, we've reached a state of equilibrium. Once the rate of the forward reaction equals the rate of the reverse reaction, A is no longer decreasing, B is no longer increasing. The concentration of A and B will be constant at that point. So if we set the rate of the forward reaction equal to the rate of the reverse reaction, which occurs at equilibrium, we can say that K1 times A is equal to K negative 1 times B. I'm going to divide both sides by A and K negative 1. So these will cancel and those will cancel. And so K1 over K negative 1 is going to be B over A. The equilibrium constant K is equal to the concentration of the products divided by the reactants. So therefore, the equilibrium constant K is also equal to the ratio of the forward rate constant divided by the reverse rate constant. The equilibrium constant K is represented by capital K. The rate constant is indicated by lowercase k. So make sure you remember this. The equilibrium constant K is equal to the forward rate constant divided by the reverse rate constant. And it's also equal to the ratio of the products divided by the ratio of the reactants. The coefficients in this case is 1. The coefficients become exponents in the equilibrium expression. Now let's work on some practice problems. Number 1, write the equilibrium expression Kc and Kp for the following reaction. Now there's two types of equilibrium constants you need to be familiar with, Kc and Kp. Kc is for concentration, Kp is associated with partial pressure. So this is the equilibrium concentration constant, that's the equilibrium partial pressure constant. Now to do this, you need to be familiar with the law of mass action. So let's say we have A plus B reacting to produce C and D. And let's say the coefficients are J, K, L, M. To write the equilibrium expression, when you see K or KEQ, it's typically associated with Kc. So KEQ is going to be the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. It's basically the concentration of the products divided by the concentration of the reactants. Now the coefficients become exponents in the equilibrium expression. So that's the equilibrium expression for this reaction using the law of mass action. Now let's do the same thing for Kc and Kp. So Kc is going to be equal to the concentration of the products divided by the concentration of the reactants. And then the coefficients will become exponents. So there's a 2 in front of NH3, so we're going to put that on the exponent of NH3. And this is going to be to the first power, and for H2 we have a 3. So that's how we can write the equilibrium expression for Kc. The square brackets indicates concentration. Now, to write the equilibrium partial pressure constant, Kp, it's going to be the partial pressure of the products, in this case NH3, and that's going to be raised to the second power due to that coefficient, divided by the partial pressure of N2, that's going to be raised to the first power, and then times the partial pressure of H2, which will be raised to the third power. So that's how we can write the equilibrium expression for Kp based on this reaction. Number 2, nitrogen reacts with chlorine to produce nitrogen trichloride. At equilibrium, the concentrations of each gas were found to be 0.15, 0.25, and 0.50 molar. Calculate the value of the equilibrium constant Kc. By the way, if you see problems that ask you to calculate K or KEQ, this typically refers to Kc. Unless specified otherwise, always go for Kc. If it specifically asks for Kp or the equilibrium partial pressure constant, then you use Kp. If you see K or KEQ, it typically corresponds to Kc. So just keep that in mind. So before we can calculate Kc, we need to write a balanced reaction. Nitrogen is a diatomic gas. Chlorine is also a diatomic gas. And this is going to become nitrogen trichloride, so NCl3. Now we need to balance the chemical equation. We have 2 nitrogen atoms on the left. We need to put a 2 in front of NCl3, so we have 2 nitrogen atoms on both sides. Now we have a total of 6 chlorine atoms on the right side. If we divide that by 2, that tells us that we need to put a 3 in front of Cl2. So now we have a balanced chemical equation. So let's write the expression for Kc. It's going to be the concentration of the products divided by the concentration of the reactants. And the coefficients will become exponents. Now remember, at equilibrium, the concentrations of the reactants and the products are no longer changing. And since we have the concentrations at equilibrium, we can just go ahead and plug it in to get the value for Kc. So the concentration of NCl3, that's 0.5. The concentration of N2 is 0.15. And the concentration of Cl2 is 0.25 moles per liter. And that needs to be cubed. So when you're plugging this in, You may want to put an extra set of parentheses in the denominator. Otherwise, your calculator may divide by this number, but may multiply by 0.25 to the third power. So I recommend enclosing that entire thing in parentheses. So let's go ahead and get the answer. So Kc is going to be 106.6 repeated. So that's the value of the equilibrium constant, Kc, in this example problem. Number 3. Sulfur dioxide reacts with oxygen gas to produce sulfur trioxide. At equilibrium, the partial pressures of each gas were found to be 0.10 atm, 0.30, and 0.45 for SO2, O2, and SO3 respectively. Calculate the equilibrium constant Kp. Well, let's begin by writing a balanced chemical equation. So we have sulfur dioxide, SO2. It's going to react with oxygen gas, O2, and it's going to produce sulfur trioxide, SO3. So all of these are in the gas phase. So to balance it, right now we have equal number of sulfur atoms, but we're going to have to multiply it by 2. Here we have 4 oxygen atoms, plus 2, that's 6, and 2 times 3 is 6. So we have 6 oxygen atoms on both sides. Let's put a 1 in front of O2. So now the chemical equation is balanced. Now, let's write an expression for Kp. So Kp is going to be the partial pressures of the products over the reactants. So we're going to have the partial pressure of SO3, and this is going to be raised to the second power, divided by the partial pressure of SO2, raised to the second power, times the partial pressure of O2, raised to the first power. So the partial pressure for SO3, that's going to be 0.45 atm. Now the partial pressure for SO2, that's 0.10 atm. And for O3, it's 0.30. So let's go ahead and plug this in. And let's put this in one set of brackets or parentheses. So it's 0.45 squared divided by 0.10 squared. And then you can take that result divided by 0.30. So you should get 67.5. So that's the value of Kp in this example problem. Number 4. If Kc for the reaction shown below is 9.6 at 300 Celsius, what is the value of Kp at this temperature? Now this is a formula that we could use to go from Kp to Kc or vice versa. But let's talk about how to get that formula. So let's say we have a generic reaction, A plus B turns into C plus D. And we're going to have our generic coefficients, J, K, L, and M. Let's write the equilibrium partial pressure expression for this reaction. So Kp is going to be the partial pressure of the products, so the partial pressure of C, and that's going to be raised to the L power, times the partial pressure of D, raised to the M power, and that's going to be divided by the partial pressure of A, raised to the J power, and then times the partial pressure of B, raised to the K power. Now, based on the ideal gas law equation, we know that PV is equal to nRT. So if we divide both sides by the volume V, we get P is equal to nRT over V. But instead of writing it that way, we can write it like this, N over V. Because concentration is moles divided by volume. So we can replace N over V with C. So we get the pressure is equal to the concentration times RT. So I'm just going to rewrite that here. So now what we're going to do is we're going to replace P with CRT in this expression. So the partial pressure of C, we can replace that with the concentration of C times RT, and it's going to be raised to the same exponent, L. So let's do the same for the rest. So the partial pressure of D is going to be the concentration of D times RT. The partial pressure of A is going to be the concentration of A times RT. And the same is true for the partial pressure of B. That's going to be the concentration of B times RT. And let's put the exponents, M, J, and K. So now what we're going to do at this point is we're going to separate the concentration from RT. The concentration of C, we can simply put it in brackets. It will be just C. But let me rewrite this over here. So keep in mind, this whole thing is still equal to Kp. We can delete this as well. Actually, let's keep that for now. So this is going to be the concentration of C, and then times RT. This is going to be the concentration of D times RT. Now keep in mind, this is raised to the L. So this is the concentration of C raised to the L, and the concentration of RT raised to the L. And then this is the concentration of D raised to the M times the concentration of RT raised to the M. You have to distribute the M to both D and RT. Now the concentration of A, we can simply just put that in brackets as well, and then times RT, and those two will be raised to the J power. And then we have the concentration of B, which is raised to the K power, times RT, which is also raised to the K power. And this is still equal to Kp. Now what I'm going to do is I'm going to break this fraction into two smaller fractions. In one fraction, I'm going to collect all of the concentration terms, and then in the other fraction, all of the RT terms. So here we have the concentration of C times the concentration of D divided by the concentration of A and B. And then let's put the exponent. So this is L, M, J, and K. Now, let's multiply these two. If we were to multiply two terms with the same base, we can add the exponents. X squared times x cubed. This is going to be x raised to the 2 plus 3, which is x to the 5th power. So if we multiply these two, we can add the exponents L and M together. So this is going to be times. So we're going to have RT raised to the L plus M. And then we could do the same thing with those two. We can multiply them, and then we can add these two exponents together, J and K. So we're going to have RT raised to the J plus K. So all of this is still equal to Kp. So we could say that Kp is equal. Now this is the equilibrium expression for Kc, products over reactants, but in terms of concentration. So we can replace this whole thing with Kc. So we have Kp equal Kc. Now that part, what happens when we divide if we divide two common bases? Let's say if we have x to the 7 over x to the 4th. We can write that as a single x variable by subtracting the exponents. 7 minus 4 is 3. So we can write this as a single RT value by subtracting L plus M and J plus K. So we're going to get times RT raised to the L plus M minus J plus K. And this is in parentheses. Now, we can define delta N as being the sum of the coefficient of the products minus the sum of the coefficients of the reactants. So J and K represents the coefficients of the reactants. L and M represents the coefficients of the products. So delta N is basically the sum of the coefficients of the products minus reactants. So now we have our equation that relates Kp and Kc. So this is the equation that you want to write down in your notes. Kp is equal to Kc times RT delta N. And remember, delta N is the sum of the coefficient of the products. Let's say Cp for coefficient of the products minus the sum of the coefficient of the reactants. Or you can write it this way if you want. The important thing is that you know how to apply it in a problem. So now, in part A, we're given Kc, and we want to find the value of Kp. So Kp is going to equal Kc, which is 9.60, times R. Now there's two R values. There's the R value that is associated with energy, 8.3145, the units of which are joules per mole per Kelvin. And then there's this R value, 0.08206, liters times ATM divided by moles times Kelvin. Now, Kp, which is described in terms of partial pressure, it's usually in units of ATM. Therefore, you want to use this R value, which contains a unit ATM. So it's going to be 0.08206, and the temperature has to be in Kelvin. So 300 Celsius, to convert that to Kelvin, we need to add 273 to it. So it's going to be times 573 Kelvin, and then raised to the delta N. So let's calculate delta N for this reaction. So delta N is going to be the coefficient of the products, which is 2, minus the sum of the coefficients for the reactants. So that's 1 plus 3. So delta N is 2 minus 4, which is negative 2. So we're going to raise this to the negative 2 power. And that's going to give us Kp. So let's go ahead and plug that in. So this is going to be 4.34 times 10 to the negative 3. So that's the value of Kp for part A. Now let's calculate the value of Kc. So how can we do that? To get Kc, Kc is going to be Kp divided by RT raised to the delta N. So that's the formula we need to get Kc. In part B, we're told that the value of Kp is 1.45. times 10 to the negative 3. And we're given the temperature as well. The temperature this time is 500 Celsius. R is still going to be the same. It's 0.08206. And the temperature is going to be 500 Celsius plus 273, which is 773 Kelvin. Delta N is not going to change because the coefficients for this reaction remain the same. So delta N is still negative 2. Thus, Kc for this reaction is 5.83. So now you know how to calculate Kp given Kc, and you also know how to calculate Kc given Kp. Number 5. Given the value of K for the reaction shown below, what is the value of K for the adjusted reaction? Or more specifically, K prime. So notice that we doubled the coefficients of the first reaction. How is that going to affect the value of K? When you double the reaction, the new value of K is going to be the square of the original value of K. So K prime is going to be K squared. Thus, that's going to be 100 squared, which is 10,000. So that's going to be the new value of K for this adjusted reaction. Now, if you're wondering why K prime is equal to K squared, here's the reason. So let's get the equilibrium expression for the adjusted reaction. So that's associated with K prime, and it's going to be products over reactants. So we have NO2 on top, NO and O2 on the bottom. And then the coefficients become exponents. So what we're going to do is we're going to factor out a 2 from every exponent. If we do that, if we factor out a 2 from 4, this becomes 2. This also becomes 2. And if we factor out 2 from 2, that becomes 1. Now this whole thing is going to be raised to the second power since we factored out a 2. Now notice what we have in here. Inside the parentheses is the equilibrium expression for the original reaction. We can see the exponents, 2, 2, 1, correlates to the exponents that we see here in that reaction. So this is equal to the original K value. So we have K prime. We're going to replace this with K. So this equals K, and then we have a 2 outside of that. So that's how we can show why K prime is equal to K squared. Now let's try another example. So what's going to be the new K value if we divide the original reaction by 1/2? So let's say the coefficients are 1, 1/2, and 1. What's going to be the new K value? So when we doubled the coefficients, it was K squared. If we multiply the coefficients by 1/2, this is going to be K raised to the 1/2. And you can prove it with the same process. So this is going to become the square root of 100, which is 10. So that's going to be the K value for this particular reaction. Now, what's going to be the new K value? Let's say if we reverse the reaction. What's going to happen then? If we reverse the reaction, the new K value is going to be 1 over K. So this is going to be 1 over 100, which is 0.01. Now, if you want to prove that, simply write the expression for K prime. So it's NO to the second power times O2 to the first power divided by NO2 squared. Now, this whole thing, since it equals K prime, we want to adjust that expression. K prime is equivalent to 1 over 1 over K prime. And if you're not sure about that, here's how you can show it. Let's put this over 1. If we multiply the top and bottom by 1 over K prime, K prime times 1 over K prime, they cancel. We get 1. And then just multiply those together, you get 1 over K prime. So based on that, this expression is equivalent to 1 over 1 of that expression. Now, how can we show that this is 1 over K? Let's multiply this part of the fraction by NO squared. That is the bottom of this fraction highlighted in blue. And we're going to multiply the top of that fraction by NO squared. So if you multiply a fraction by NO squared over NO squared, you're multiplying it by 1. You're not changing the value of that fraction. Here, NO squared will cancel. And so what we're going to have left over is K prime is equal to 1, and then that's this line in white, divided by NO squared. And I'm going to draw the fraction line that's highlighted in blue, which is this line, over NO squared times O2. Now, this expression here, where NO squared is on top, and on the bottom we have, NO2 squared is on top, and on the bottom we have NO squared times O2, the reactant side. This is the equilibrium expression for the original K. So we can replace this with K. So that's how we could show that K prime is 1 over K when you reverse the reaction. So now that we have the value for K prime for this one, let's try a new one. So let's say we have this reaction, but the coefficients are 6, 6, and 3. What's the K value for this reaction? So if we compare it to the original expression, the reaction has been reversed. So we know K prime is going to be 1 over K. And if we compare the coefficients, we've multiplied the reaction by 3. Whatever you multiply the reaction by, you need to raise K to that exponent. Since we multiplied it by 3, we're going to raise it to the third power. So K prime is going to be 1 over K cubed. So that's 1 over 100 to the third power, which is 100 times 100 times 100. That's 1 with 6 zeros. So that's a million. A million is 1 times 10 to the 6, since we have 6 zeros. If we move 10 to the 6 to the top, the exponent changes from positive 6 to negative 6. So this becomes 1 times 10 to the negative 6. So that's the new K value that corresponds to this reaction. So now you know how to calculate K when the reaction is adjusted. Either you reverse it, multiply it by 2, or multiply it by half, and so forth. 20 moles of NaCl is placed inside an empty 4-liter container. At equilibrium, 8 moles of Cl2 was found to be in the container. Calculate the value of Kc for this reaction. In order to calculate Kc, we need to find the equilibrium concentrations for every species in this reactant. We don't have that. What we need to do is write an ice table. So at the beginning, the initial value of NaCl can be calculated. Notice that we placed 20 moles in a 4-liter container. So to calculate the concentration, it's moles divided by liters. So we have 20 moles of solute divided by 4 liters. So that's going to be 5 moles per liter. That's the initial concentration of NaCl. Now the container is empty, so we don't have anything for NO or Cl2. So we're going to place a 0 there. Now, because the products are equal to 0, the reaction has to shift towards the right. It cannot shift to the left. And so Cl2 is going to increase by some amount 1x. Now, notice the molar ratio between NO and Cl2. It's 2 to 1. So if Cl2 increases by x, NO is going to increase by 2x. And NOCl is going to decrease by 2x. As the reaction shifts to the right, the products will increase in value, but the reactants will decrease in value. So if we add the first two rows, this is going to be x, 2x, and 5 minus 2x. Now the concentration of Cl2 at equilibrium is x. And we also know that at equilibrium, 8 moles of Cl2 was found to be in the container. So the concentration of Cl2 at equilibrium is going to be 8 moles divided by the 4-liter container. So it's 2 moles per liter. So now we know the value of x. X is equal to 2m because they're both equal to Cl2. So now we can find the equilibrium concentrations for everything else. For NO, it's equal to 2x. And since x is 2, that's going to be 2 times 2. So NO is equal to 4m. Now we can also calculate the equilibrium concentration for NOCl, which is equal to 5 minus 2x. So that's going to be 5 minus 2 times 2. So that's 5 minus 4. So it's 1 mole per liter at equilibrium. So now that we have the equilibrium concentrations for every reactant and product in this example, we can now write the expression for Kc. So products over reactants, on the product side we have NO and Cl2. And for the reactant side, we only have NOCl. The coefficient for NO is 2. The coefficient for Cl2 is 1. And for NOCl, that's 2. So now let's plug in the values. So for NO, that's going to be 4. For Cl2, it's 2. And for NOCl, it's 1. So 4 squared is 16, and 1 squared is 1. 16 times 2 is 32. So Kc in this example is 32. And that's the answer. Carbon monoxide reacts with oxygen gas to produce carbon dioxide. At equilibrium, the concentrations of O2 and CO2 are 0.10 and 0.75 moles per liter, respectively. So we're given Kc. What is the concentration of CO at equilibrium? The first thing we need to do is write a balanced chemical equation. So we have carbon monoxide reacting with oxygen gas, and it's going to produce carbon dioxide. So to balance it, we just need a 2 in front of CO and CO2. And so we have Kc for this reaction. 10 to the third is 1,000, so this is going to be 4,000. Now, we have the concentrations of O2 and CO2 at equilibrium, so we don't need an ice table to find the equilibrium concentration of CO. Let's write the expression for Kc. So it's products over reactants. On the product side, we have CO2, and on the reactant side, we have CO and O2. The coefficient in front of CO2 is a 2, so we need to put that here. And for CO, it's also a 2, and it's a 1 for O2. Now, Kc is 4,000. The equilibrium concentration of CO2 is 0.75. And the value for CO is what we're looking for. So let's call that X. And the concentration for O2 is 0.10. So let's cross multiply. So first on the left side, we're going to have 1 times 0.75 squared, which is 0.5625. And on the other side, we're going to have 4,000 times 0.1, which is 400, multiplied by x squared. Now we need to divide both sides by 400. So 0.5625 divided by 400, that's 1.40625 times 10 to the minus 3. So that's equal to x squared. So now we got to take the square root of both sides. And so x is 0.0375. So that's the concentration of carbon monoxide at equilibrium. Number 8. At a certain temperature, ammonia partially decomposes into nitrogen gas and hydrogen gas. Ammonia was added to an empty container until the partial pressure of NH3 reached 0.85 atm. At equilibrium, the partial pressure of H2 was found to be 0.45 atm. What is the partial pressure of NH3 at equilibrium? Well, first we need to write a reaction. So ammonia is decomposing into nitrogen gas and hydrogen gas. And we've seen this reaction plenty of times, so we know how to balance it. Now, we have partial pressures at equilibrium and initially, before the reaction begins. The 0.85 atm, that's the initial partial pressure of NH3. And then we have the partial pressure of H2 at equilibrium. Whenever you have information at equilibrium and before the reaction begins, you need to write out an ICE table. Initial, change, equilibrium. So initially, the partial pressure of NH3 is 0.85. We don't have anything else in that container, so the partial pressure of the products is 0. Now, our next step is to determine what direction the reaction is going to go. Is it going to go to the right or to the left? Now, anytime any one of the products is 0, the reaction has no choice but to go to the right. Because if you don't have any products, it cannot go to the left. Otherwise, these will become negative. But since we don't have any nitrogen or hydrogen gas, they can't react together to form ammonia. So the reaction has to go to the right. As the reaction goes to the right, we know that the products will increase in value, the reactants will decrease in value. So this is going to be positive 1x, because it's a product, it's going to increase. And this is going to be positive 3x. Let me write that better. The 1:3 ratio is based on the molar ratio that we see here. As the reaction shifts to the right, the reactants are going to decrease in value. So we're going to have a negative sign for the change. This is going to be negative 2x. So we have negative 2x, 1x, 3x, based on the molar ratio of 2:1:3. Now let's add the first two rows. So at equilibrium, the partial pressure of NH3 is going to be 0.85 minus 2x. For N2, it's going to be x. For H2, it's going to be 3x. Now that we've completed the ICE table, what should we do next? Now looking at the problem, we're told that at equilibrium, the partial pressure of H2 was found to be 0.45 atm. So we can write that. At equilibrium, we also know that the partial pressure of H2 is equal to 3x. Therefore, we could set 0.45 atm equal to 3x, and that will help us to solve for x. So let's divide both sides by 3. So x is going to be 0.45 divided by 3, which is 0.15. So that's the value of x. Now that we have that, we can calculate the equilibrium partial pressure of any one of the reactants or products. So our goal is to calculate the equilibrium partial pressure of NH3. So that's going to be 0.85 minus 2x. So let's replace x with 0.15. 0.85 times 2 times 0.15, that's 0.55. My handwriting is terrible today. So this is the final answer for this problem. That's the partial pressure of NH3 at equilibrium. If we want to find the equilibrium partial pressure of N2, it's simply x, which is 0.15. And if we want to, we can calculate Kp for this entire process. So Kp is going to be H2 raised to the third power times N2 raised to the first power divided by NH3 to the second power. It's products over reactants. So we know the equilibrium partial pressure. Actually, I wrote this wrong. This should be the partial pressure of H2 raised to the third power times the partial pressure of N2 to the first power divided by the partial pressure of NH3 to the second power. So the partial pressure of H2, that's 0.45. For N2, it's simply x, which is 0.15. And for NH3, we calculate it to be 0.55 based on that expression, and we need to square it. So Kp is going to be 0.0452. So that is the equilibrium partial pressure constant if we want to find it.